Hi everyone, so this is a review for chapter 10 revision quiz set 2. So this is the responses I've collected. There's only 34, less than half. It's getting lesser and lesser, not a good sign. So I'll be discussing questions 16, 17, 18, 19, 20. Basically all the questions that went over 40% for now. Okay, so let's move on to question 16. Okay, question 16 says if capital R is 2 times of small r, what is the ratio between intensity of capital R over intensity of small r? So let's try to figure it out. Okay, so the relationship that you know here is that R is equals to 2R. Then what you want to find out is IR over I small r. This is the relationship that you want to find. So we know in general, intensity is the power per unit area. Power per unit area. So if this is a spherical, we are looking at the whole spherical wave over here. We are looking at this sphere as a whole. So the power will be coming from the source. Okay, so the power is actually coming from the source. Okay, let's call this power generated by sound source. Okay, then this power is being spread out evenly over the whole spherical area. If the distance is smaller, like this small r over here, then the area will be smaller. Then the power or the energy per unit time will be shared between this evenly over this small area, small spherical area over here. But if it's a capital R, means like it's a bigger spherical area, then the energy per unit time will be shared evenly across this larger spherical area for capital R. Okay, so I'll just write generally for now. So it's divided by A. Okay, if P is the power generated by the sound source, then A will be the spherical area then. Okay, this is for if your sound wave is spreading out spherically, the spherical area. This is what we know. So we will know that later when we do this ratio, we'll need to do the power for the source. Okay, do they have the same source? Well, the source is this black dot over here. So as you can see, this blue spherical area and this yellow spherical area, they are sharing the same source. It's like it's the same speaker, just that this one is you are detecting the intensity like let's say 5 meters away from the speaker, whereas this one you detect it 10 meters away from the speaker. So you want to check the intensity when it's at 5 meters, you compare it with when it's at 10 meters. Just compare the power per unit area. So they share the same speaker here, they share the same sound source. In that case, I will just say the power generated for R will be the same for the power generated for R because they have the same sound source. Therefore, I just call them P. Okay, but let's do it slow. Let's do it like this first. Over AR. Okay, just that this is a subscript of capital R divided by P small r over AR. Okay, this thing here comes from the formula here. Okay, so once we have constructed that, let's substitute in whatever you know. We know that the capital R, the power for capital R and the power for small r are the same because same sound source. Okay, just to be very clear, because it's the same sound source. Okay, with that being known, okay, now the rest will be just algebraic manipulation. So P over R, not A capital R. How do you find the spherical area? 4 pi r squared. So this one will be 4 pi r squared. then you divide it with, again, it's the same P, because same sound source. Area will be 4 pi. Now it's small r squared. Okay, it's just substitution for the surface area, spherical surface area. Now if we continue, we can flip things up a bit. P over 4 pi 2r. Okay, it's being written here. Capital R is equal to 2 small r. So now it's a matter of bringing these things together. Times, okay, I flip the bottom up, multiply by P over 4 pi r squared. Okay, now I continue it here. The P and the P you cancel. So we are left with 4 pi r squared on top, 4 pi 2r squared at the bottom. So now if I expand it out, then it becomes 4 pi r squared divided by 4 pi 4 r squared, which if I take it out the 4, then you have 4 pi r squared minus 4 pi r squared. Now you can potong some stuff, then you will be left with 1 over 4. So 1 over 4 is also 0.25. And that will be our answer for this question, 0.25. Okay, moving on to next question. Next question, question 17 says, two people hear the same sound at the same distance. So if you see people say hear the same sound, what it probably means is that it's the same sound source. Then from the same distance, from the source of the sound. So means by they have the same R. What happened to the pen? Suddenly very big. Okay, so this person number 1 here, it listens for 1 second. Whereas person number 2 here, the area is twice the area of person number 1. So you can think of this person here has a smaller ear, and this person probably has a larger ear. Okay, smaller ear. This one has a larger ear. Besides having a larger ear, this second person here also listened for twice the amount of time. Before this, it was 1 second for person number 1. Now it's 2 seconds for person number 2. Okay, so that's the differences. The difference is in area and the amount of time spent to listen to the sound. So now they ask for the intensity of the sound. It's again intensity of the sound. Then you want to compare between person number 1 and person number 2. So I1 and I2. Okay. So let's try to solve the question then. Okay. So please be very clear that when we talk about intensity, talk about power per unit area. Okay. So let's draw a spherical shape. Okay, let's say this is your a sound wave. Then there's at the center there's a sound source. So person number 1, he will be probably listening at here. So person number 1 has a smaller ear. So this is person number 1. So person number 2 has a larger ear. Then this person number 2 is listening here. So this person number 1 is listening it for time which is 1 second. Okay, I label it T1, whereas this person over here, T2 equals to 2 seconds. So that's the differences between them, but they share the same distance. Same distance is by from here to here, it's r. Then from here to here, it's also r. Okay, you can call it r1 equals to r2 equals to r. Okay, so I hope you understand the situation now. So let's try to solve the problem. Okay, we know that we want to compare intensity between 1 and 2. So let's recall what's the formula for intensity. Intensity is power per unit area. Okay, so now you might be thinking, is this the same power, the power of the sound source? I mean from here, power of the sound source. Well, there's a better way of thinking about it. Okay, basically you want to you change the power to be the power absorbed by the ear. Okay, means by, let's say, I have flat, I don't know how to explain it, but your area of your ear is this big, right? You want to see this area here receive how much power. Okay, you want to receive how much energy per unit time, receive how much power. Okay, so how do you know how much power that is received by this ear? Well, you know the intensity can be the intensity at this distance here. Intensity at this distance can be find out using this formula here. I equals to power of the sound source divided by the area. Then you know that this power of the sound source divided by 4 pi r squared. Then you get for every single unit area how much power is passing through it. So by knowing this per unit area how much power is passing through it, you can know, if you know the area of it, then you can multiply the number of unit area, and you know how much power is passing through the ear. Okay, before that, if you calculate using this formula here, you are calculating how much energy or how much power, how much energy per unit time is passing through a unit area. Let's say per meter square, you have 5 watt passing through it. Per unit meter square, you have 5 watt. So let's say your ear here is 0.5 meter square. So you receive 2.5 watt because your ear is half of the unit area. Then your ear will only receive half of 5 watt, which because the intensity is 5 watt. So you receive half of 5 watt, then you get 2.5 watt. You get the unit area, how much power is passing through a unit area, then you times the area of your ear. Then you get how much power is passing through your ear. Okay, it's a bit complex concept. Okay, if you still cannot understand, just tell me in the WhatsApp group or Telegram. Okay, so the intensity of person number 1, okay, the intensity of received by the ear of person number 1 will be the power is the power received by person number 1 divided by the area of the person number 1. I mean the area of the ear. This is also power received by the ear of person number 1. How do you find P of person number 1, the power? We take the power produced by the sound source, divide by the area, the total spherical area over here. Then we get a per unit area, power per unit area. Then we multiply by the area of this little ear over here to know how much power passing through this ear over here. Okay, so after that you multiply by the area of this guy's or this girl's ear area. Okay, it's weird, the formula. This is the area of the ear of person number 1. Then you divide by person's number 1 area of the ear. Okay, sounds weird. This one up here, you are trying to obtain power passing through the ear of person number 1. This one is the power of sound source. This one is the spherical area. So this thing that you're obtaining here is the intensity of sound r distance away from the sound source. I'm a bit worried you cannot understand the concept. This is a bit quirky. Source. Okay, whereas this one is the area of the ear. Of person number 1. Then this will be the intensity of sound received by person number 1. It's an interesting question. Okay, so if you proceed, you will see that many things will potong. This one can cross each other out. So you are left with the power of the sound source divided by 4 pi r squared. So this is the intensity of sound received by person number 1. Well, if you can think a bit farther, think a bit faster, then you will see that for person number 2, you will get the same answer. Okay, this is the power received by the ear of person number 2, and this is the area of the ear of person number 2. Okay, let's see why do I say they are the same thing. Okay, let's do power divide by the area is still the same area. Now this one is A person number 2, and then divide by A person number 2. Okay, if you are fast, you can straight away just cross these two things out. But let me prove to you slowly why I can still get the same answer. Because we know just now over here that the area of this person number 2 is twice the area of person number 1. Person number 1 has a smaller ear, person number 2 has a larger ear. So what will happen is I can continue by making this to become 2 times the area of person number 1 divided by the 2 times the area of person number 1. Okay, then you can see the 2, I can cross out the 2 over here. Then what you are left at the end is, wow, this is a long question, 4 pi r squared times area of person number 1's ear divided by area of person number 1's ear. So you can see this thing is exactly the same as this thing. Okay, they are identical. Let me put it on a bit. Okay, this one is identical to this one. So we can straightaway say that they are equal to I of person number 1. Therefore, the conclusion we can make here is the intensity of person number 1 is equal to the intensity of the sound received by person number 2. So they are the same. The answer is they are the same. Well, if you want to think just logically without doing any maths, well, they are hearing the same sound and they are standing at the same distance away from the sound source. How can the intensity be different? Okay, you have a larger ear. It means by you receive more energy per unit time. But intensity is per unit area also. So you have bigger area, you have to divide by bigger area also. So even though you have bigger power, you also have bigger area to divide. So the bigger the enlargement of the power and the enlargement of the area will cross each other out. So basically nothing changed for the intensity. Okay, that's a more conceptual way of thinking about it. But it's still the same sound. If same sound, same distance, intensity should be the same. Okay, so that's question 17 for you. Let's move on to question 18. Well, question 18, it's related to question 17. Okay, it's the same situation. You have two people, then it's the same sound, so means that the sound source is the same sound source, then same distance. Okay, let me write it down again. Same sound source. The next one is same distance. Okay, now this person number one also listen for 1 second, number two listen for 2 seconds, then at the same time the person number two has area which is twice the area of person number one. Exactly the same scenario like question 17 just now, but now they are asking for the power produced by the source of sound. How does the power produced by the source of sound compare for the two cases? Means by the power produced by the source of sound for case number one and the power produced by the source of sound for case number two, what is the relationship between them? So they are asking the power produced by source number one, what's the relationship with the power of source number two? Well, if you are really careful with what we have been saying just now, you immediately know that the answer is again same. Why? Because it's the same sound source. So if you have the same sound source, you will have the same. This is asking for the power produced by the sound source for these two cases. For the two cases, they are using the same sound source. So of course the power will be the same. It's like using this speaker for Ali. Then you use the exact same speaker for Akao. Then they are asking whether the power produced by the speaker is what's the relationship for the power produced. They are asking for the relationship between the speaker in case 1 and speaker in case 2. Speaker in case 1 and case 2 are the same speaker. So the power produced by the same speaker should be the same. So the answer is definitely the same. There's nothing to prove. It's the same sound source, so the power produced should be the same. Okay, so that's for question 18. Wow, long question. Question 19. Question 19 says, let me zoom in a bit. Okay, a string is clamped at both ends. Clamped at both ends means by both ends are actually nodes. And it's plugged so that it vibrates in a standing wave between two extreme positions A and C. This is position A, this is position C. So this is the one of the extreme position. Follow my cursor. This is one of the extreme position. Then this is another extreme position. So the standing wave will oscillate between this extreme and this extreme. Okay, so if you can't imagine how a standing wave looks like, again, third time recommending, go Desmos, go key in the equation, go look at the animation by yourself. Then you will know how a standing wave oscillates. So basically it oscillates between this extreme and that extreme. We call one of it extreme A, the other one extreme C. Okay, now they ask, when the string is in position B, the instantaneous velocity of points along the string is, wow, okay, when the string is in position B. So means by it is not at its extreme. So it means by my string is actually over here. Okay, you need to understand how standing wave looks like. Only you know that the string looks like this. When these particles oscillate back to this position B, every place along the standing wave, you will see a straight line. Everybody is at the equilibrium position. Okay, this particle is oscillating up and down between position A, B, and C. So the question asks, if the particle at this position goes to B, then what will you see for the instantaneous velocity along at all points along the string? If they ask for the instant velocity here, instant velocity here, instantaneous velocity here, instantaneous velocity here, here, here. Are they the same or are they different? What is the instantaneous velocity at all these positions? Instantaneous velocity means the vibrational velocity, the particle vibrational velocity at all these positions. Are they the same or not? Okay, so well, I believe this question should be able to think about it. Okay, so let me zoom out a little bit. Okay, so like I said just now, if this particle is at position B, then the wave will look something like this. Okay, then let me label all the position as well. You have two nodes at both ends, and as you see, there's 1, 2, 3, 4, 5 nodes in between. So let me roughly do it. 1, 2, 3, 4, 5. Okay, so these are the 5 nodes in between. Then also you have an node, of course, in between. 1, 2, 3, 4, 5, 6. So this is your line over here. So they ask for the instantaneous velocity of points along the string. Means by what is its instantaneous velocity here, what is its instantaneous velocity here, what is its instantaneous velocity here. Is every point having the same instantaneous velocity, or every point having different instantaneous velocity? Okay, so for that you probably have to go to Desmos and go try and figure it out. And if you go look at Desmos, you will see that the particle at this position, particle at this position, this position, this position, this position, this position, this position, and this position will all be at rest. It's not moving. Whereas the particle over here, it can be moving upwards. Then this one will be having a greater velocity here, greater velocity here, lesser velocity, lesser velocity, lesser velocity, something like this. Then you also see that this part will have greater and greater velocity, and you have smaller and smaller velocity. Okay, so you see that at different points across the position of the wave, you see different instantaneous velocity. Here at the antinode, the velocity have to be the highest because it needs to travel a larger distance to reach its amplitude. If you are near the node, you only need to move a little bit distance to reach your amplitude. So the particle here can move slower, whereas the particle at the antinode, you have to move faster because there's a greater distance to travel, and they all reach the peak at the same time. So if they all reach their amplitude at the same time, here you need to travel a bit slower, here you need to travel the fastest. Only they can arrive at the peak at the same time. Okay, so that's the idea behind it. So as I've drawn here, all of them will be having different instantaneous velocity. So the answer will be, the instantaneous velocity will depend on the position. If you are nearer to the antinode, you have greater instantaneous velocity. Okay, you are now, all of them are at equilibrium position. If you remember from SHM, the velocity at the equilibrium will be maximum. So all of them are at their maximum velocity. But because at antinode you have greater oscillation, if you have greater amplitude of oscillation, you need greater instantaneous velocity at the antinode compared to somewhere near the node, You don't have that much oscillation. Your oscillation has a small amplitude. So you don't need to have very great instantaneous velocity. So the instantaneous velocity varies. It depends on the position. So that's the answer for question 19. For question 20 is the exact same situation, just that right now they ask if the string is in position C. So means by the particle has already reached here. So just now it was here, then now it moved down to here. Okay, if that's the case, you probably imagine that the wave will look something like this. Nope, not this one. The wave will look something like this. All of them reach their respective peak, reach their respective amplitude. Okay, so this is the maximum. Every particle over here are reaching their maximum right now. They are at their maximum displacement now. Okay, it's really difficult for me to draw to explain the whole thing again. If you need, you have to refer back to my previous videos on standing wave versus progressive wave. I've explained quite clearly there. So for this situation here, this particle is at its maximum. Okay, it's oscillating between these two positions and it's at its maximum now. Okay, probably you need an equilibrium line to make things clear. Oh, what a bad equilibrium. Okay, so for this particle here, it is also at its equilibrium because this is the oscillation that it is having. Then if you are talking about this particle over here also at its maximum because this is its oscillation. If you talk about let's say this particle over here memang tak bergerak, it never moved. So you can consider it is at its maximum. That is its maximum, that is also its minimum because it never moved. So all points along the wave, any point here, 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 every point along the wave, all of them are reaching their maximum. Just that some is reaching maximum in the positive region, some is reaching maximum at its negative region. So remember, all of these are particles, right? If they reach their maximum, think back to SHM. If particle is at its maximum displacement from the equilibrium position, what will be their velocity? Their velocity will all be 0. Why all of them will be 0? Because they reach their maximum means by they need to U-turn and go back to their equilibrium position. All of these particles here will now need to go back down right now. They all need to go back down. They want to come back down to equilibrium. This one they need to come back up. Come back up. Come back up. Come back up. They want to go back to equilibrium. So before these particles here, they go up and reach the maximum. Then now they need to come back down. So before this, they are going up. Then now they reach maximum. Now they want to come back down. So before this go up, after this come down means by you change direction. If you want to change direction, you have to stop for a while. Only you can change direction. That's how every U-turn works. To change direction, you must stop for a while. Change the opposite direction. To change the opposite direction, you have to stop for a while. So all of these places here, every particle here are actually stopping for a little bit. At this instant, they are all stopped for a little while. Then after that, they change direction. This one move down, this one move up, this one move down, this one move up, this one move down, this one move up. Okay, so at this particular instant, every particle is at rest. So every particle is at rest. So the instantaneous velocity at everywhere will be 0. They are all at rest. All these particles, they have Vy of 0 right now. All these particles, they have particle vibrational velocity of 0 meter per second when they are at their respective amplitude. Okay, so that's 0 everywhere. If you can't imagine, again, I recommend go Desmos, key in the equation and find it out yourself. Okay, so I've discussed question 20, question 19, question 18, question 17, and question 16. A total of 5 questions. So that's all for chapter 10 revision quiz set 2. Thank you very much.